Hi folks, welcome to a module on randomization schedules in pragmatic clinical trials. I'm Liam, and I'm joined by my co-host Angela. This podcast was created by the HDRN Pragmatic Trials Training Program at Western University in London, Ontario.
Thanks, Liam. We often talk about randomization in broad strokes, simple, block, stratified. But what really matters for trial operations is how those ideas get turned into an actual sequence of assignments that sites can use day to day. That's where the randomization schedule comes in. At its core, the schedule is the operational playbook. It's not just what method you chose, it's how that method becomes a list of patient 1 assigned to treatment arm, patient 2 assigned to control arm, and so on.
And the form we're highlighting today, the checklist you'll see linked in the video description, walks trialists through documenting those choices step by step. It covers the rationale, the sequence generation, who has access, how to conceal the assignments. Basically, all the details that would be needed to include in your trial protocol.
Okay, let's talk through some of the big buckets on the form. The drop-down menus, randomization unit, and allocation scheme are where the real customization happens.
Right. First up, the randomization unit. You've got two choices, individual or cluster. Individual randomization is what most people think of. Each participant gets randomized on their own. Cluster randomization is different. You randomize whole groups like clinics, schools, or hospitals all at once.
Once you pick the unit, the allocation scheme options change. For individuals, you'll see simple randomization, the classic coin toss. Block randomization, that's about keeping groups balanced after every block of participants. Stratified randomization, adding in important factors like sex or site. Then there's minimization, which is a covariate adaptive method for fine-tuning balance, and outcome adaptive randomization, which can shift allocation probabilities mid-trial.
If you choose cluster as the unit, the menu updates with schemes that work at the group level. Simple randomization still exists, but you also see stratified or blocked randomization for clusters. Pair-matched randomization, where you find similar pairs of clusters and randomize within each pair. Covariate constrained randomization, which balances several cluster-level factors at once. And then the heavy hitter, stepped wedge randomization, where clusters all eventually get the intervention just at staggered times. Plus, yes, even minimization can be applied at the cluster level.
Once you pick one of these allocations, the form fills in an overview of what it is, when it works best, risks and limitations, and safeguards. That way, you've got context right there in front of you.
And right below that, you'll see steps in brief. These are the action points for implementing the allocation in practice. And you can even jot down your own trial-specific notes in the boxes. So the form doubles as both a guide and a working document. Okay, so let's bring this to life with a concrete example with a hypothetical study called Remote Visits for Type 2 Diabetes, a multi-center, individual-level randomized controlled trial, or REVID for short.
Right. REVID asks basically if adults with type 2 diabetes can book video or phone GP visits, in addition to usual in-person care. Do we see better A1C and fewer acute care visits over 6 months?
Design-wise, REVID is a parallel arm RCT, one-to-one individual randomization, 10 outpatient clinics, centralized allocation, and, yep, variable block sizes to keep balance while avoiding predictability.
Participants are adults 18 to 65 years with type 2 diabetes and baseline HbA1c greater than or equal to 8.0%. The intervention is the option for remote GP visits plus monthly nurse-led coaching through a secure app. The control arm is usual care. Primary outcome is change in HbA1c at 6 months. Secondaries include missed appointments, ED visits or hospitalizations, and patient-reported access and satisfaction.
Now let's walk through the steps in brief, exactly like the form does, so you can mirror this for your own trial.
So, step 1. Revid goes with a 1-to-1 allocation ratio with Arm A, which is a remote visit option plus monthly nurse coaching, and Arm B is usual care.
And, just to be super practical, those ARM definitions are operationalized in the intervention manual and linked to electronic health record order sets. That way, enrollment staff aren't guessing what ARM A actually means.
Next, specify block sizes. Because it's 1-to-1, permissible sizes are multiples of 2. Here the team chose variable block sizes of 4, 6, and 8.
Yeah, varying block size cuts down on predictability. The central system randomly picks the next block size within each site as recruitment proceeds.
Step 3. Revid stratifies by outpatient clinic. There are 10 sites, so each site maintains its own balance as it enrolls over time.
No extra baseline strata here. Things like baseline HbA1c get handled in analysis, subgroups, rather than as strata that would multiply the number of sequences.
Step 4. The schedule lives in REDCap's randomization module. Under the hood, it uses a Mersenne twister pseudo-random number generator.
The reproducible seed is 48 plus the clinic ID, 1 to 10. So each site sequence is reproducible and site-specific. Only the trial statistician holds seed custody.
Step 5. For every allowed block size, the system samples from all balanced permutations, like AABB, ABAB, BABA, uniformly at random.
And because we're stratified by clinic, those permutation draws are independent by site, so sequences naturally diverge across clinics.
Step 6. For each clinic, the team pre-generates a sequence long enough for projected accrual plus 25%, just to be safe.
Block sizes and within-block permutations are randomized. If a site unexpectedly outgrows its target, they can regenerate with the same parameters, but only with documented rationale and approvals. Paper trail matters.
Step 7. The list itself stores block IDs and positions, not participant info.
The participant identifier gets appended only at the moment of randomization. That prevents foreknowledge, tampering, and, honestly, awkward human temptations.
Step 8. Master sequences go into an access-controlled repository. Role-based permissions. Statisticians have read-only. Enrollment staff cannot view upcoming assignments or block sizes.
Full audit logging, timestamp, user, site, action, and those logs mirror to the trial master file. If you're ever audited, you'll be grateful for this. This trial is open label, so there's no participant blinding, but outcome assessors and analysts are blinded to protect the outcome evaluations.
Step 10. The protocol and SAP store the rationale for randomization and allocation concealment, spell out the unit and ratio, list block sizes, and record software with version number and the seed policy.
Implementation details live there too. Who can trigger allocation, contingency plans if a site exhausts its pre-generated sequence, and the approval workflow for regenerating sequences.
There is also a clear description of how to handling incomplete blocks, meaning what to do if enrollment at a site stops before finishing a block of randomization. In this trial, incomplete blocks are left in the database, documented, but not reshuffled.
And they run non-actionable balance checks, aggregate summaries, after about 50% enrollment, strictly descriptive, not used to tweak the scheme mid-trial. That keeps the conduct clean.
So, yeah, big picture. The beauty of the form is that it turns all of this into a repeatable recipe, from the seed rules to access control. So your trial's randomization is transparent, auditable, and boring in the best way.
Boring is beautiful when you're running a trial.
Could not agree more. If you found this content helpful, hit like and subscribe, and turn on notifications so you don't miss future content. Until next time, this is Angela and Liam signing off.